Yeah. Okay. So thanks for sticking around. So last lecture I will talk about random dynamical systems in the context of critical decision complex systems and their early warning signals. So people who actually asked me to talk about that, and it's also maybe the context of the fact that I flag on the slides all the time that I'm part of a consortium
by European Union that studies this specific topic.
So we have a group in Europe, 8 nodes in 5 countries, 15 PhD students, and a group that meets twice per year or more, working on this kind of problems. So our
point of view, our input in that is from random dynamical
systems, also on some other aspects of that. So what I want to do is I want to present some introduction into
this topic actually. So
critical decision in complex systems is a very popular topic, and I hope to convince you and explain to you why
this is the case, and also maybe why it's an
interesting topic. Strange noises. Do you get strange noises?
He says it.
Good. Okay, so I hope to convince you not only that it's an interesting topic,
but also there's a lot of things
to be done.
Sometimes the speaker picks up your
Oh,
voice,
okay.
sometimes not.
Okay.
Maybe is it better like this? Okay. Good. So I'd like to say something about
Complex systems.
So, question like what's
Complex systems.
It's been very popular and it's maybe it's very important, but it's also a bit of a hype of the question like what is it precisely? I remember I went to talk to some person at the funding council in the UK for grants, and this person was the expert in complex systems, and I asked the person, say, what are complex systems? And then this person couldn't really tell me what complex systems were, and I thought it was interesting because that's a difficult type of problem.
And then she
referred to certain people
that were doing something that she understood to be
complex systems. Okay. Good, but what is the context? In physics, I would say the description of states of systems and the transition between them, like the bifurcation theory, is a central theme. It's not just a mathematics topic, it's really in science. And so we have 2 types of systems, I think, which are well understood or well studied. The low degrees of freedom, dynamical systems, few degrees of freedom, like mechanical divisors, simple lasers, we have a few variables, and we
describe them in terms of ODEs
and things like that. And we can do bifurcation theory for these low-dimensional systems. This is one part of dynamics, and that's well understood. And also in terms of transition to state. And then there's, on the other side of the spectrum, there is high degrees of freedom systems, statistical mechanics.
So this is the
opposite end of the spectrum. There we have like 10 to the 24 particles interacting. And we maybe think of fluids or gases or materials. And strangely enough, or remarkably enough, we can also do things there.
So this is a theory
in statistical mechanics of phase transitions, and this has been one of the big successes of physics in the 20th century to really make progress there. And I remember actually being in a talk by Michael Fisher one day when he gave an overview
over this actually
remarkable theory of phase transitions and how this
really has an impact in understanding
materials. But the trick here is that as we can work with few equations, we can deal with this. There's some tricks that we can work with many equations and many particles by some kind of like probabilistic approach. So there's some funny way we can deal with this one and we can do this one. They're on the opposite end of the spectrum.
Anyway, so we have this dichotomy somehow in understanding. And so where are the complex systems? They are anywhere where we're not in these two situations. That's how I say the complex refers in some sense also to the fact that we cannot deal with it. So what is complex research? Intermediate degrees of freedom. Not 3 degrees of freedom, not 10 to the 24 degrees of freedom, maybe 25. Biomolecules, a good example, for instance, where we have not enough degrees of freedom to just do statistics. Maybe heterogeneous rather than homogeneous problems. So, for instance, again, in biosystems, like in the brain or something like that, we have non-inhomogeneity of the connections, and where statistical mechanics works very well is where we have homogeneity. We have gases where we cannot really identify the particles. There's materials which are very nicely ordered, and we use all this homogeneity to kind of solve problems here. If it's very inhomogeneous, you're basically into trouble. Another aspect of complex systems is maybe open rather than closed systems. So in dynamical systems, as we've learned from celestial mechanics, we basically usually study things that are closed. We have a system which is closed, is not interfered by anyone. And in complex systems, often one encounters problems that are open systems. It means that some information comes from the outside and maybe some things leave the system. And this is, for instance, a big problem in a so-called non-equilibrium statistical mechanics, where people also don't know how to do it. Another typical problem in complex systems is non-autonomous systems rather than autonomous systems. So systems that are explicitly time-dependent. And of course, everything in the world is explicitly time-dependent. Things change, it's not always the same. And so most of the modeling that we understand is that where basically our behavior is constant, and we just hope somehow, and then we take mathematically limits of time go to infinity, just assuming that nothing changes. But this is of course not right, and of course they're complicated system where the rules of behavior change while we're ongoing, and this is difficult to understand. And finally, taking sort of noise into account. So have some kind of equation of motion with a certain lack of accuracy. So you see, what I just made is a list of things that are not in these two categories. And this, of course, the complement is huge. And I think, in particularly, in the current context, somehow these complex systems are important because we have a whole wave of science happening, of quantitative science happening in areas where they weren't before, basically because there are methodologies and there are computers and there's data and there's cheap sensing and so on and so on. So where new areas come up, where you really have to deal with these things. You cannot really say like, well, biomedical sciences modeling is just 3 degrees of freedom, and it's also not a homogeneous system with 10 to the 24 particles. It is societal sciences where people study all kinds of things. This is also another problem. So what's happening is that we have quantitative methodologies entering these fields without somehow a proper understanding of the mathematics. So what happens is that many things are done by, formulating models and running them on computers and simulating them. And that can be done, and sometimes there's also a challenge. So the challenges here, I would say, are in 3 areas. I think they're all quite important: the biomedical sciences modeling, economical societal modeling, including markets, opinion dynamics are important. The politicians want to manipulate us, so what we think, energy, environment, climate change, internet. But also very importantly, I think it underpins big data science. And we can collect lots of data, but the question is, again, what do we do with all this data? Does it mean anything to us? And unfortunately, again, we have to rely on some kind of models that make sense of the data that we collect. And they come from a world where all these issues that I just mentioned are real issues. So we cannot really avoid that. So there is a huge opportunity for this field. But of course, it's also so big that it's maybe not just one field. It's just like a collection of all open problems that are just open. So we cannot maybe address them all at the same time. Good. So I particularly want to talk about a topic called, it was introduced maybe, or popularized, definitely by Malcolm Gladwell. And he wrote this book, which is says here already, the international #1 bestseller. Actually, Malcolm Gladwell writes lots of bestsellers about all kinds of things. And this is our tipping point. And so what's the idea of the tipping point? Is that there are remarkable things in society that it seems to be that some phenomena shift very quickly, much more quickly than you would expect, and also in an unexpected time. So you have some changes that are gradual in society or in something, but some changes are very quick and apparently for no good reason. And he collects some of those ideas and examples, and he says like, well, what happens is there's some mechanism by which things hold up, and at some point it just basically all changes very rapidly. And of course, this is some kind of expression of what physicists already know, that this could happen, of some kind of phase transition or bifurcation. But I think that Gladwell really very successfully introduced this as a concept that is relevant for everyone, not just for physicists doing magnetism or something like that. So, the first time I came into contact with critical transitions in complex systems is when a colleague of mine in Amsterdam, Alian Homburg, I was visiting him and he gave me a paper to look at. And this was a paper called Early Warning Signals for Critical Transitions. It was by Martin Scheffer and another few people, biologists from Wageningen University, which is an agricultural university. And Alian asked me, what do you think of this paper? And I had a look and said, well, it sounds kind of interesting, but it's like some kind of bifurcation theory with some application of bifurcation theory. I said, yeah, because, you know, some people don't know exactly what it is, and the mathematicians maybe are not too excited about it because there's some back of the envelope calculations there, but maybe, is there something in there? And so we work on bifurcation theory, and it looked like application of bifurcation theory, and the question was, is there something in there that's interesting? So Martin also wrote a book, and where he basically explains, around the same time, this was 2009, these ideas. And so they established in the ecology group some kind of idea of applied bifurcation theory. And so the history is that Martin Scheffer worked on lake quality, the water quality in lakes, and there were some problems with lakes that get very troubled. They get very dark and they get dirty. And the question is like how to kind of manage such a lake. And Martin successfully understood that it is actually some kind of bifurcation problem. And he understood there was a hysteresis in the problem. And by doing more or less the counterintuitive thing that you should have been doing, he could kind of push himself out of the hysteresis into the right branch. And we'll see these kind of examples soon popping up. And Martin really made this into some kind of culture, and he really managed to kind of explain to many people that this is important. And Martin is extremely successful in bringing this message to people in a visionary way. And Martin always says he's not a mathematician, but he likes to use his mathematics to solve real problems. And he's extremely successful. So in 2012, then I organized, together with Martin Rasmussen and Greg Pavliotis, a meeting in Imperial College called Critical Transitions in Complex Systems, where we just brought a group of people together. So the picture is some kind of reminiscent of what a critical transition could mean in terms of a climate change to London or something like that. It's quite a dramatic picture. So the idea is like, is there some kind of mathematics that helps you understand why things change in complex systems in a certain way, like for instance in the weather, others that cannot be understood by existing methods. Of course, we have a bifurcation theory, we have a theory of phase transitions, and the question is like, is that enough or not? And of course, it is true that there are many problems that can be solved by methodology that already exists, but there are also many problems that can't. Okay, so here I looked up on the Web of Science, it's the Thomson Reuters website, on tipping points and early warning signals and critical transitions. And you see here some kind of exponential growth. So this started in 1998 with about like 40 papers, go to more than 300 papers in 2016. And citations goes here from, well, something less than 198 to more than 7,000 in 2016. So it's just some measure of actually that these ideas are sticking. So there's an increasing number of people that are interested in this topic. Tipping points, warning signals, critical transitions. Okay, so what is the quintessential paradigm of the critical transition? It's something that many people that do physics or mathematics have probably seen. So we have a certain kind of like state of the system versus the system state versus conditions. And so we have certain kind of transitions where they're just smooth because the state curve is basically smooth. So if I change a little bit my conditions, my system changes slowly. But it can also be that we have a certain kind of kink developing in this graph. And then what could happen is if this graph goes this way, and this is a typical hysteresis curve. And so the problem with this is that if I'm on this curve and I'm here, then there's nothing to go to other than to this point, schematically. And if I push back, I will stay on this one because this one is a stable one until I end here and I will just suddenly jump up. So this is the quintessential idea of critical transition, which of course is well known in physics as hysteresis. So there are a lot of magnetic materials that behave like this. If you do an undergraduate degree in physics, you all see this. So but the nice thing of this, of course, is that you have this kind of like quick drop in condition. And so the idea was like, can we model society in this form? Or some problems in society in this form? And of course, now there are many applications where these kind of curves then are produced from data or from otherwise. And so here, for instance, this is a study, this is from Martin Scheffer's article here in Science in 2012, where there is a study of attitudes, and you see here some kind of like passive, public attitude from passive to active, and this perceived seriousness of the problem. So this is in opinion dynamics. The question is like, if you push people, will they become very active or do they remain passive? And how does this dynamics go? So it's not really a smooth curve. People have the tendency to suddenly jump into become very active. They stay very active, and at some point they then drop their involvement. That's just an example. Another example from climate science is the relative oxygen concentration in the atmosphere, and as a function of input of redundant from volcanism and other resources. So it's very important for us that we have a rich oxygen atmosphere, otherwise large mammals and animals cannot live. And so apparently you can jump into this region, but we could also crash out of it. And this would be catastrophic for our life as we know it. And here's another popular application, ice cover. So we have so-called the ice-free Earth and the snowball Earth. And this is all possible, and apparently people understand that there is some kind of like curve here. So we here have the partially ice-covered Earth, but it's well possible to go to the ice-free Earth. And apparently people believe that we're here. I can't really say much about it. But it's also possible to go to a snow-covered Earth if you fall off the other thing. And if you're on the wrong curve, then we're in big trouble because we cannot just jump back up. We have to kind of go in a complicated way. Okay, so that's hysteresis. Okay, so now what is the classical early warning signal that people know about? And this is basically what's explained in Martin Scheffer's book. And this is something that those of us who know something about bifurcation theory, just for ODEs, is all very understandable. First of all, so-called critical slowing down. So they have an idea that if you come close to a point which undergoes a transition, so they think in terms of the hysteresis as a critical point which disappears, which is, by the way, typically something for one-dimensional systems. And this is actually, I will come back to that, but all these pictures are one-dimensional, and those of us that do dynamical systems know that you cannot just reduce all dynamics into one dimension. So it is a caricature, and it's not clear that if you have an S-curve from data that you can just jump back and forth between these things if it's a complicated projection of reality. Anyway, if you come to such a critical point which loses stability, we of course know there's an associated exponent or eigenvalue of the fixed point or equilibrium point, which will become close to the eigenvalue close to 1 or to 0, and it will lead to some kind of slowing down of behavior near that point. But also in an experiment called resilience, if I perturb the point near its equilibrium, if you have a very stable equilibrium, then it goes very quickly back to its state. And if the eigenvalue is very close to instability, then it doesn't really come back so quickly. And so this is what they call critical slowing down. So they have some kind of experiment that they do to test this. So this is one early warning signal for bifurcation. And the other ones are more statistical, and they're kind of related to this. So if you think of a system which also has some noise, and and usually they assume that because they understand that the reality is much more complicated than just a simple ODE or something like that in low dimensions. So they say, well, there's lots of other things going on, and also this resilience is tested actually by the noise. So if you have an equilibrium but it's not stable, you can actually see it already from the data. And so you can do then some very simple autoregressive model where you just say, well, this is the exponent of the equilibrium. You get some kind of behavior. This would be e to the lambda t, not x to the lambda t. E to the lambda t. And so you get a very simple linear behavior with a noise term, which we assume to be Gaussian, for instance. And then we can very easily do some computation on take the expectation of this. We can calculate the variance. They see the variance also depends some on the noise level, but also on this eigenvalue in a very trivial way. And then you see that if the eigenvalue goes to 0, which is a sign of this instability, then the variance goes to infinity and autocorrelation goes to 1. So what they do is then they measure, where possible, the variance of some if you have a complicated signal, or they measure autocorrelation. And they call them all kind of warning signals. So either it is this slowing down behavior, its variance increasing rapidly, or maybe autocorrelation. And then what they did in this article, which was kind of interesting, they basically came up with a lot of examples where this happens. So here you see somehow how this happens in a model context. So you see there's a simple idea of the model, but you see that the data looks very hedged. Why? Because they always add a little bit of noise, because otherwise they think that probably the model isn't really realistic enough. And here you see some things which are quite obvious, some kind of like here the lack autocorrelation, because it widens, of course, if the potential gets flatter. And you see some kind of aspects of the time series. So they can see obviously that there are some aspects reminiscent of these behaviors. And here's another behavior where you have such a hysteresis curve, some noise, and they say, well, you have some potential of flickering, of jumping back and forth between these nodes, and then you have a unique stable state on this side. So these are things, the terminology that people use for this. And so surprisingly, so that with such a very limited set of tools, there's now a whole list, and you cannot read it, but there's a whole list here in this paper of applications where people use these kind of warning signals technique to see if there's something happening and whether it's successful or not. And so the gist of it is that in many cases this is successful, to think of it like that, and in some cases inconclusive, or maybe it doesn't really work. But there are many examples from chemistry, physics, engineering, tectonics, climate, ecology, epilepsy, physiology, microbiology. So the idea is that somehow they propagate this idea of these bifurcation ideas, and this idea of looking for a bifurcation point by criteria, by experimental criteria or data analysis criteria, is feasible. And of course, this is a very attractive idea that we can actually achieve this. So here's some examples of this. Here it is an example which is the problem of overharvested population. So if you have overharvested population, you have a signal, and it tends to suddenly drop because your population just dies out. And here they measure, for instance, autocorrelation. And what you see here is that it basically increases. So they say this is a good measure. On the signal, you don't seem to see much what's going on, but for the autocorrelation, they claim you can see this. And here's a epileptic seizure coming up. And again, here they measure the variance of the signal. And again, it seems to be that if the variance goes up, this is an early warning signal for an onset of an epileptic seizure, according to this graph. And here we have a greenhouse icehouse transition. And here again, kind of a big drop in the climate dynamics with a strong increase of the autocorrelation function. So there seem to be, that's interesting of this paper, of these papers, there's a few papers that do this, that they collect a lot of different examples that seem to convincingly show that maybe there's something going on. And as a last item, there's also some story about patterns, about resilience in networks, how they are organized, and also in spatial patterns in ecology, where you, for instance, can see whether we're towards like a desertification regime, where maybe you lose all the vegetation, you go into a desert or something like that. So the question is, like, can you see these things coming by the vegetation patterns? And again, there's some claims that this is indeed possible. Okay, so what is the objective? The objective is the website that they already have. So there's a website made by people that, around the group in Wageningen, and it's called the Early Warning Signals Toolbox. It is implementing those ideas and saying, like, look, we provide you with tools to analyze this data and to understand what's going on. So they have a website, earlywarningsignals.org. And a lot of the things that I just explained are also explained on this website. And so the idea is clear, that they think that there are universal ways of understanding at least certain classes of dramatic events, and that these dramatic events can be predicted by using certain methodologies, and they try to kind of propagate those along all areas. So the interesting is that the group of Scheffer and co works in ecology, aquatic ecology, but they now also work on Twitter data and on lots of other stuff. So they have quite a large group of people working on all kinds of data analysis. But this, of course, is a wishful thinking, because the challenge is that, of course, most models for this critical decision that I just prescribed are rather naive. And of course, one can get a little bit more complicated, but it's rather naive. In particular, there's no reason to assume that problems are reducible to these very simple pictures. And those of us that study bifurcation theory, we know that it can be much more complicated than that already. And the mathematical analysis of the models and the development of the warning signals also, I think, has ample room for improvement, even in the one-dimensional case. So even in these simple models where we have some noise sitting on a one-dimensional dynamics, you can probably do a lot better than has been done already. And also, it's interesting to notice that it appears natural and also maybe advantageous to consider models that incorporate noise. So for those people, and I think in reality, they understand that the model as it is probably not realistic enough without the noise. Let me see if I can. It is a bit unstable. Wait a second. Goes on and off in a minute. Yeah, the connector is not. I think there's something. It's in this one. Another connector, maybe there's another connector. Let's check. Oh, this is not good. No. It's been working the other days. Oh, do you have one? Sorry for this. Yeah. Oh yeah. Good. Sorry about that. Okay, another criticalization, and I'm grateful for the early warning signal. Anyway. Good. Yeah, the incorporating the noise. Yeah, so there's a nice anecdote that Scheffer was telling me the other day, is that so apparently among geriatrics doctors, it's well known that testing resilience for older people is a good indicator of their life expectancy. So the idea is that if someone's old and you give them a little push, then if they recover quickly from this push, then they're kind of in a good shape. But if they don't recover from the push, then their life expectancy can be a problem. So you can predict how well people are doing in a very complicated situation. It's just testing the resilience. So this is actually something that among many applied scientists has got hold as a reasonable thing. But he also mentioned that, of course, it's unethical to go to old people and give them a little push to see if they sustain the push. But he said the nice thing is that nature provides these pushes, because nature provides random input to everyone constantly. So we don't need to push people around. We just need to see how they behave in reality. And the noise in the reality actually provides constant perturbations to us, and we can just measure the response from what we are. So we don't need to do the resilience experiment. But it's important aspect that we have this noise in there. And the noise also helps us to get information out of the system. The noise is not something that actually makes it more hard to understand. It actually helps us to understand. It provides the dynamics of the system with noise includes information about the resilience and the robustness of the behavior in some sense. Whereas if you just sit in an equilibrium point, for instance, and you stay there, you can see nothing from the time series. It's just a stationary point, nothing happens. But if you're perturbed away and you come back to the point, then you actually have extra information, is that you kind of have a certain kind of stability. And so there's certain advantages of using noise, and I think so that's important. So it seems to be a kind of unrealistic here to work with models that don't have noise, although of course the pictures that people use are more deterministic, but then they like to put some noise on top of it. And so why is this? I think it's also because there is actually maybe a lack of mathematical theory of such models with the noise. So what do? Well, you take the deterministic picture. Anyway, so I think there's a real challenge here for mathematicians to contribute to the theory in aid of more applied scientists. And in particular, I think bifurcation theory for random systems is still only in early development. So that's what I've been talking about the last few days. And maybe I can add actually an anecdotal story about how I first came to think about these problems, which was again precisely because of some applied scientists. There was a physiologist in one of Imperial College's hospitals who at some point contacted me and says, well, you work on bifurcation theory, isn't it? Yeah, can we talk to you? I said, okay, that's great. And the person works on apnea. This is the blockage of the breathing. And they had complex signals for EEG and ECG, and they wanted to basically know, can we from a time series see whether someone will have an event which is an unhealthy event. And so they understood somehow that, smartly enough, that maybe that this was a bifurcation theory type of problem. But when I heard about the problem, this many years ago, I realized very quickly that, yeah, of course, this was a kind of problem that should be addressed by people that claim to do bifurcation theory. The problem is that we don't really address this problem. So we don't really know how to recognize a bifurcation from a time series, or whether we're close to a bifurcation. And this was really a missing point somehow. And of course, some things have happened, so it's good to see that there's now such a development, and that I can be part of this. Good, so what's there already? Well, we have classical bifurcation theory, which is basically largely based on singularity theory, and sometimes called some branch catastrophe theory. So there is a good understanding of how zeros of smooth functions behave on the variations of parameters of those functions. And this is a basis of a beautiful classification of phenomena in dynamical systems, which is very, very useful. So it really leads to classification, not just a description. And now you can, of course, this bifurcation theory is so that we believe you compute the state of a system in an autonomous system, and you fix the parameter, and then you change the parameter and you fix another fixed state. And now, of course, there's an idea that maybe if you vary the parameter, adiabatically, it's very, very, very slow, that more or less this bifurcation theory should be correct. So I don't know many people that really study this properly, but it seems to be obvious that this should be okay. I know that Christian Kuhn did some analysis in slow-fast systems along those directions, but it's not so surprising that these things should kind of work. But beyond the adiabatic limit, if I have a parameter and I just fast move it, then of course the dynamics of the parameter is going to interfere with the dynamics of the system. So you can't really say, well, it's the same if I just have a very slow moving parameter or move it fast. If I move it fast, then the system will not settle down in an attractor, and I already changed it, so the whole dynamics will change. So so if having non-autonomous systems or random system, we cannot just approach it from this theory. It doesn't necessarily apply. And in system mechanics, it's important. It's also we have a bifurcation theory with so-called critical exponents for phase transitions, which is also precisely some kind of like early warning signals. Precisely in material science, people know how certain curves critically approach a phase transition, and that's really used, and this is the way these kind of transitions are classified. And so the whole idea of, say, radialization and critical phenomena in statistical mechanics is precisely based on the same thing. But of course, we saw already that these theories, they apply to a certain class of systems, but not necessarily to the ones that we're interested in. Okay, good. So I dwelt on generalities, and what I'd like to do now is to go back to the same old example, more or less, that I've been talking about the last few days, and to see if he can make any sense of early warning signals in the kind of bifurcation that we have seen there. And so let's look again at this pitchfork bifurcation example. So this is an example, put some noise on it. It's a bounded noise. And we have, in the deterministic case, either 1 or 3 solutions, just a pitchfork. So this was, and the transitions like alpha is equal to 1. And then when we put some noise on it, then we saw that basically this becomes some kind of attractor. And we have some kind of region here where we had some discontinuous change in the support of the stationary measure. So we got some kind of pattern picture with a certain abrupt change of support in invariant measure over here. And so this was basically the what we saw already. Now the question is like, can we make sense of reasonable way of predicting such transitions, and how do we go about that? So what we found is that interesting information is hidden in so-called finite time Lyapunov exponents. So people may know what the Lyapunov exponent, I already introduced it earlier. So the Lyapunov exponent is basically the average derivative along an orbit. And so usually in order to have existence of the Lyapunov exponent and so on, we need to load time go to infinity. So we compute basically this behavior. This is the flow, linearized flow along our orbit. So we write down a variational equation, for instance. We compute the spectrum, and then we average basically over the length of the trajectory. And so almost surely in a Goddard component, these things exist and are independent of initial condition for full measure Z. No? But now we can also calculate these finite time things. So in engineering, people have done it for some time, and maybe mathematicians is less common, because the problem is, of course, now if I just calculate it only for finite time, I'm not so sure. Of course it exists, because it just calculates finite objects, but I don't know really what it means. We don't have beautiful theorems about these things. But it turned out that they are actually quite useful, and that one can write some theorems about them, which I will not do now. But in the meeting, I think that Martin Rasmussen will say something about relationship with the finite time Lyapunov exponent, the so-called dichotomy spectrum, which is a uniformly hyperbolic spectrum. So the importance that what we measure here is basically how we have a spectra of derivatives in a certain context operating. So this lambda will be a random variable, and it has this kind of limit, but I can just compute these things. So we can have a look at such computation. And so here what happens is there's a computation of the spectrum, and I have to tell you what the numbers are. So 0 is here. And so this is negative, and this is for alpha is 0.7. So this is somewhere over here. So we have some measure over here and over here. So what happens here, we had the uniform contraction, and what you see is from the finite time Lyapunov exponent for a certain time, and I can't read the time, maybe 30, is that you get a certain distribution of these exponents. If I let the time go to infinity, then this distribution will narrow and go to Lyapunov exponent. But the important thing is that there's also something, there's some more information for the dynamics about the distribution of these exponents. For instance, you have a support of these exponents. In this case, the support of these exponents is completely in the negative half line. That means basically you have uniform contraction. Now, if you then change the parameter, and I have to stand back to see what it is, so this is 0.8, then what happens is that this graph moves somewhat to the right, and here it moves to the right, and at some point, what happens, it will move over 0. But it still could be true, because we know that if you here go, it goes over 0. If we know for the one-dimensional case that the Lyapunov exponent is negative, because it cannot be anything else. But what can happen is that we still have part of the spectrum in the positive half line. So that means that we have some expansion in the system, but it doesn't dominate asymptotically. But of course it's important, and precisely it's associated to this non-uniform attractivity that I have in this region. And so non-uniform hyperbolicity is characterized by the fact that if you look at the finite time Lyapunov exponents, that they sit partially in the positive and partially in the negative half line.
These red curves are given by theory, or
no, the red curve is a fit by Gaussian, which is very poor. Yeah. So we did actually Son did this computations just last night. Actually, we were arguing and playing around with these examples. Yeah, so we have also calculations from the Lyapunov exponent if we come from this direction. So I know here that I have a change of the Lyapunov exponent spectrum because I have a 0 eigenvalue here for the equilibrium point, and then we have positive eigenvalues, and actually all these eigenvalues are basically picked up. So because I have a repulsive equilibrium sitting here, is precisely the reason why I get positive contributions here in the spectrum. So there was a discussion earlier about what is the change in dynamics in this region, and Carroll and Flanderly saying that, well, we have a unique attracting point attractor. So basically there's no difference in dynamics. If you look at the finite time Lyapunov exponent, which is observable, so this can be just computed, you can actually see there's a difference just from these numbers. And it means something dynamically because we have these potential excursions from synchronization as we saw. That's how this is a sign for that. And this is computable. But now we will go to the other side, and we also have a bifurcation. Here we have a set value bifurcation where this set suddenly explodes into a larger attractor. Here, a stationary measure sits in a confined region and it explodes to a larger region. And again, this is actually accompanied by some bifurcation point of a fixed point on the border that disappears. It's a saddle-node bifurcation, and that also triggers a 0 exponent. So also here we have a 0 Lyapunov exponent spectrum, which is completely in a negative half line with support. And then what happens, it opens up support here, and immediately here we get full support. So here you see also a picture of that. So here is 0, and here we are down the line. We move back with the parameter into the system, and we see that we also get here positive contribution here, 0, so we have positive contribution here, just past bifurcation point. So we can see from this Lyapunov exponent spectrum these things happening. Okay, so these were computed with the equation of motion. We just run a simulation. Now the question is, can we also get this from experimental data? So I asked this last night to Yuzuru. I said, Yuzuru, can we do this? And he said, come on, of course, I can do everything. So, so here is an experiment where we just got the time series from the simulation, and then without looking, we try to kind of reconstruct the dynamics so that we can actually construct this finite time Lyapunov exponent spectrum. So what do we need for that? We need to reconstruct the derivatives. Because in the data series, we don't have a derivative, but we have lots of points on the attractor. Now, with the points on the attractor, with the recurrence plot, one can actually reconstruct the relationship as in a statistical way. So this is a recurrence plot, and you can find the attractors, and if we zoom in, we can see that we get very good agreement. So this is actually just a diagonal. So if we look at bifurcation, we look how the curve goes. The black line here is the true curve for the equation. The purple line is the noisy input we get from the data, and the red dots are the averages over these lines, and you see that they fit very nicely the true curve. That means we can now calculate the exponents basically from feeding the data and reading off the numerically obtained derivatives from this curve. So we can actually reconstruct the Lyapunov exponent data from the data. So and this was done in just a few hours less sleep. But I think it was a very nice experiment. It said, like, you know, we can have a theoretical idea of doing data analysis, but can we really do it practically? Is this practical with straightforward methods? And so I think that at least in this kind of very toy example, we could see that we can actually do something which makes some sense. So it is possible to get such observations of Lyapunov exponents even out of just a time series. Yeah, we haven't tried. Yeah. Of course, there will be some challenges if we make it more complicated. I think the first test is to see if you can, in principle, do this with reasonable computation from a set. So we could probably give Yuzuru lots of data and not tell him which parameter values we are, and he will be able to tell us what we're doing. And he will also be able to create this characteristic graph for the finite time Lyapunov exponent. And what I also would like to emphasize is that, I don't know if people notice this, that the shape of these graphs, so these graphs are from this approach, and there's another graph of distributions, they're from this approach. And they look markedly different.
So what if you go, from below, if you do this same computation and keep on going beyond the
Yeah, here you have a mixture between positive and negative exponents.
Yeah, and what if you go further?
Yeah, at some point you jump, because then you jump into...
So it drops to...
Yeah. Yeah. So the negative exponent, the exponent is always negative.
Right.
Yeah.
Relative finite value.
Sure. Yeah, but that's precisely what you see here. So here we pushed over the line, and you see that basically this more or less continuously evolves. Yeah, it should need not be continuous, of course, because you suddenly drop open a huge part of the phase space. So you can suddenly, so here we have continuity, but you will typically not have continuity if you have an explosion of your behavior, because you have no idea what dynamics is here. It could be anything. So, but one thing that I remarked also is that the shape of the distribution is different. And so this the distribution fits reasonably well this Gaussian fit, which is actually not so visible. And here you could see very clearly that it actually doesn't fit at all. And so that's also kind of interesting, because you could ask, well, if I approach this bifurcation point or this bifurcation point, can I see any difference in this Lyapunov exponent spectrum? And you can, and it's not so difficult to see that it should be, because here the zero eigenvalue sits in the middle of the distribution, which is actually highly populated. That's why the graph actually has a lot of eigenvalues basically going up to 0 is like highly populated, and we don't have a tail touching the 0. It's really the mass that really hits the 0 Lyapunov exponent. Whereas in this example, it's basically the tail of the distribution that will start populating precisely the boundary point. So there's a signature also on this finite time Lyapunov exponent for the bifurcation, because this bifurcation is a quite different one than this one, and you can see that actually in the signature of the finite time Lyapunov exponent. So of course, if I just say to calculate the Lyapunov exponent, I can't really see anything. I just see a negative number. It doesn't tell me anything. Anyway, so there's a certain kind of attempt by us kind of to propagate these Lyapunov exponents as a measure for bifurcation, and this was also done in the pitchfork example, the one to show that basically the additive noise does not destroy the pitchfork bifurcation of Van der Lee, and actually the first time we argued that we also used the finite time Lyapunov exponents.
So why did you use pitchfork rather than Sutherland?
Oh, just because I did it in the course now. We can, of course, also do for Sutherland nodes, yeah.
This pitchfork bifurcation may not be called quicker transition, because it's a continuous change of the...
Yeah, I think, yeah, I agree. Of course, one is interested in these kind of first order phase transitions, which are actually global bifurcations. And in the one-dimensional theory, these global bifurcations arise because an equilibrium disappears. So there's, I think, some confusion here, is that in the one-dimensional theory, yes, to have a global bifurcation, you need to disappear. Some state needs to disappear. So they talk about, for instance, in these texts about good transitions, about you have alternative states, and then one of the states disappears. But of course, in higher dimensions, we can just have a change of stability and not a state disappearing, and we have the same effect. So there is a certain, I think there's a good argument to make that if you really want to understand these things in higher dimensions, you have to think of more like homoclinic or heteroclinic connections, and so rather than about equilibria bifurcating, because that's typically. But I personally think that in order to understand the whole plethora of bifurcations, one has to study bifurcation in this context. Of course, one is interested in these kind of first order transitions where you jump, but I think it sits in a whole, the other things are also not understood. So I think I can understand from the application point of view, you think it's more dramatic to talk about dramatic bifurcation, but I don't think that we should restrict to that necessarily. As a definition of the topic, it's very strange to kind of cross out everything which is not a first order transition. This has never happened in phase transitions in physics either, that people say we only do first order transitions because they're more dramatic. So I think that's not the issue. And I think there's still some things maybe here also, that even though this bifurcation looks smooth, it's not so smooth as it looks like, but the noise, I have, for instance, bounded behavior, and suddenly I have behavior that just has much larger excursions. So even though the underlying picture is smooth, it's actually not so smooth with the noise. So one has to be a little bit careful to conclude whether or not something is actually a critical, a drastic change or not a drastic change. So my idea, yeah, so my program more is like, let's study bifurcations in such context, and let's worry about later whether or not these are abrupt or not. Okay, so here's some more examples of the computations showing that this can all be done. Okay, I want to talk about one other example that I also looked at with Yuzuru some time ago, that we have a logistic map. We have a logistic map in the so-called period 3 window. So we know we have this period doubling root, and then we have some kind of like chaotic regions. And at some point there's a period 3 window where we have just 3 things and not much else. So we have complicated dynamics in the bifurcation diagram, logistic map, and period 3 window, the stable periodic orbit. But in between we have very unstable dynamics which you don't see in the bifurcation diagram. And so the interesting thing here is if you put some noise on it, is that we can lose stability from these stable states, but we end up in a very unstable region. So if you think about the two-point motion that we discussed the previous days, you see that there may be lots of opportunities to destabilize from the synchronized state. So here there's some numerical plot where you have a change of parameter value, and we have here the points. So there's like 3 regions. There's one region which has negative Lyapunov exponent and negative and bounded noise. So we have bounded regions on which you have the behavior. Then there's an opportunity to start interacting with the 2 states, but we still have negative Lyapunov exponent, but we have positive positive finite time Lyapunov exponents popping up, and they think that you can see that in here. There's a kind of some spectrum popping through 0, and there's some point where we really have leading Lyapunov exponent also being positive, meaning that we don't have synchronization. So we have a complicated transition between basically very stable dynamics, some kind of stable dynamics on average with intermittency in some sense, noise-induced intermittency. And then we have basically really chaotic dynamics. And you see here some kind of examples of this, where we have like, in a 2-point plot, for instance, you see here that we, in the very chaotic case, we have some invariant measure which sits in a non-trivial way in the 2-point motion. In this case, it should sit on the diagonal, but of course we have some excursions. Here we have slightly more excursions. The interesting thing here is that so the desynchronization in this example is much more than in the pitchfork example, because in the pitchfork we have only one saddle point, and it's kind of difficult to get there. But here we have lots of unstable behavior on the diagonal, so it's very easy to see things going out. But in the same way, still the invariant measure, the stationary measure, will sit just on the diagonal here. So even though you see other events, they're still there. So the question is again, can we see such kind of things in reality? And I think it's interesting to look at this plot. This is basically some kind of statistics of excursions from the diagonal, from synchronization. And there's some interesting plot here, because this is kind of some kind of random thing. This is another diffusion behavior that we have, a uniform diffusion. And it's a log plot. And now we have some kind of very strange peaks here. And the question is like, where are they coming from? So this is something that Didier Sonnet called Dragon King, and he says this is the reason, or a part of a reason for financial crashes. So you have some kind of anomalous phenomena that are occurring much more than statistically would be expected. Now the question is like, where would these things, where would they come from? And they precisely come from these so-called bubbles from attractors. Yeah. Y minus x is just in a 2-point plot. Y minus x is the distance from the diagonal. So this is the density versus the distance from the diagonal. And this is in the log plot. So this goes logarithmic here. And this is also logarithmic. Yeah. So this is the power law, but then somehow we deviate from the power law very pronouncedly. So why do we deviate from this power law so pronouncedly? It has to do basically with the underlying 2-point dynamics. So that can be seen. So here we have the 2-point picture, x and y. X equals y sits on the diagonal, and we have 3 attractors, and let me schematically put them at 3 points, and then we know we have these invariant lines. And so we see at 3 distances, we see a peak. And you can actually, if you now look carefully, you can see that from this picture we get precisely to see those lines. And so here we have a line, and at 3 separate distances, because these points are not the same distance, we get the 3 separate distances, the potential to kind of sit on something which is stable. So we have blowout from this line, and we go then to these levels. And in these levels, we measure then the difference. So we see that we have pronounced peaks, we have 3 pronounced peaks precisely referring to these levels. Of course, we don't visit it a lot, but we visit precisely those 3. So you see in this experimental plot, just of the statistics, we see that we have these peaks. Now the interesting thing is that from the statistics point of view, if I take the time limit to infinity, then these peaks will die down. Because we know that they actually don't statistically are visible. So because statistically everything, all invariant measures is on the diagonal. So it's only, there's actually no excursion whatsoever. So this whole graph will actually kind of start coming down. But for the finite time picture, you see it. So it's again a kind of an indication that from the random dynamics, we can actually somehow see interesting behavior from the data that really is explained by the underlying dynamics and is not explained by the statistics at all. Statistics gives you basically this kind of lines. It doesn't give you such strange behavior on top of it. So this was first seen by Didier Sonnet, and he called this Dragon King, and people have similar deterministic models that have similar phenomena related to so-called blowout bifurcation of an attractor. And you see these things. But I think it was a very nice example that you could see also in this random dynamical system, which is conceptually much easier than the models that they usually use, which has many components. This is actually a very low-dimensional example. The noise takes care of everything, and you get precisely the right phenomenon for this thing. So this is, again, critical transition material. Stock market crash could be the thing. If you have events which are not statistically expected, this is precisely the type of things that people are also interested in. And so it makes sense to do this plot.
Horizontal axis is the distance from the diagonal.
Exactly, yeah.
Where is it? So the 0 is the diagonal.
Yeah.
0 is diagonal.
Yeah, yeah.
But this is a log scale.
This is a log scale. Yeah, this goes 0.01, 10 to the minus something here. 10 to the minus 6 here. This is 0.01. It's all very small. Here's 0. So you have a certain, so of course, because we have the noise, we have a certain kind of range in which points are seen. But of course, if I integrate more and more, what will happen at some point is this whole graph will come down. Because things will condense. Now the question, of course, is that if we can find some way in which we can describe these things in some invariant way. So it is statistically not visible, but it is visible in any experiment, basically, in the right scale. Okay, so these, of course, are the phases 2 and 3. Is the phases where we have escape. This is actually in the case where we have negative Lyapunov exponent, and this is where we have positive Lyapunov exponent, and we see basically much more diffusion behavior here. And so here should probably the things don't die out here, but here they must die out because of synchronization. Yeah. And these things should be studied more actually somehow. We haven't really done everything yet. What I wanted to do is actually to show that in such a simple example as here, that we really have phenomena that are measurable, that are potentially of interest, that have been observed by people or have been used to explain certain phenomena, and I think they're tractable more in the random dynamical systems context than they are in the deterministic context. And for deterministic systems to create such statistics, you need to go rather high dimensional system, whereas here really just a one-dimensional system with some noise can do it, and the noise really takes care of introducing the complexity in some sense. Okay, so I will pause quickly. Let me just try to finish this part. So the quality of the early warning signals depends on the state of the bifurcation theory. I think that's something that I truly believe. How can we predict something if we don't understand the phenomena? So I think it's quintessential that we don't just do or just phenomenology of like potential things that we can measure, but also try to understand the underlying mechanisms so we can trust them. And well, especially in random systems, because there's basically an absence of bifurcation theory, it is important to develop this, but also to devise concepts and theory that leads to computable objects that can be used in analysis, say for early warning signals. I think it's important that we, and hopefully things that are better than simulation, that are faster than simulation, that's really essential. And of course, I think we're just at the starting point, really. People haven't looked enough at it to understand what should one say about a random dynamical system to characterize its dynamics. And I've been warning kind of like just stationary measures is not really telling us enough about the dynamics. We don't really look under the hood enough. And what to do in higher dimensions is a problem. So what happens, of course, we know that in deterministic systems, there are nice methodologies like center manifold reduction and all kind of other things that we know how to kind of map high dimensional things, often in low dimensional things. If we have noise, it's not so clear if we can actually do this. It's not so clear that if we understand one-dimensional bifurcation with noise, that this helps us a lot to understand high-dimensional systems with noise as well. So that's potentially problematic because we're so used to it, and we think that we can understand complicated things by simple models, and it may well be that this is not so easy in this context. Okay, I will stop here for a moment, and then, yeah. Yeah, sure. The final part of the lecture will do two things. I will talk about something slightly besides the point, but it's also important, the importance of including noise in complex system analysis, not only because maybe it is necessary, but maybe because it's advantageous, and also for the mathematics. I would like to give you an example where adding noise actually helps the mathematics. So I was making the point before that when we do modeling, there's a certain point of like that we have to choose what kind of model we use and for what kind of purpose. If we kind of have the wrong model, we may get the right phenomena, but we may not be able to prove anything because it's just almost impossible to prove something. For instance, we are familiar, maybe Professor Kukuba's work also in the homoclinic bifurcations, that there are certain questions that just can't be answered if you work with homoclinic bifurcations because there's so much fine detail in the things that we can never find out everything about it. So in a model with homoclinic bifurcation, some questions cannot be asked because the answer is always negative in the sense that you need to have infinite information to say something. So it is, I think, important when we do modeling that we don't end up in such a situation that we have a model by which we cannot really answer the question we really want to answer, because then we get stuck and focused on this kind of like issue where maybe we can actually get around that issue without losing the sensibility of the model. And sometimes noise can work like that. Sometimes noise can help us to, for instance, if you have a dynamical system which we know have very intricate behaviors, which makes it very difficult to understand what's going on, sometimes adding a little bit of noise can actually clarify the situation enormously in such a way that we can suddenly prove a theorem that says something very precisely, whereas beforehand we couldn't really say much at all. We can just say that it's all very complicated if you look into it and it looks all very complicated. And I think there is a certain problem in dynamical systems that we have got stuck in some of these problems that are very hard to push one forward. Let me give one example. We are very interested in the deterministic systems and do ergodic theory. And proving ergodicity and proving properties of invariant measures and so on is a large part of the business. If I have a deterministic system and I add a tiny bit of diffusive noise, then this question is completely a non-question. It's completely clear that we have a unique invariant measure, which is the back continuous. So that it really kills the sport completely. Now people say like, oh, that's not fair. And you just basically change the system and now everything becomes trivial. That's not really fun. But now the question comes up, and now suppose you do that, can you say anything about the dynamics? And the problem is then actually, even though you know that everything is ergodic, even if you know that you have nice properties statistically, you can still not really understand the dynamics. This is what happens often in these random systems. So there is a certain point is that when you get focused on some kind of questions that are hard, they're very interesting and very worthwhile understanding, but they don't necessarily help understanding the next step. So these days now, I think about these things. I sometimes ask my colleagues, I say, look, you work on these problems, and suppose you can prove everything that you wanted to prove, and you're really successful. I say, what do we now know about the dynamics? I say, well, because I have systems that I can immediately say what my invariant measures are, and I don't know anything about dynamics. And this is a bit of a problem, because it's a very interesting problem, but it has really sucked a lot of energy into it. And there is, you know, also in ergodic theory of dynamical systems, most of the effort goes into one-point motions, basically, and it's not the dynamical behavior. And even though it's non-trivial and very interesting mathematically, I think there's a certain issue that if you want to understand systems better, you have to ask the question also, like, suppose that the ergodic theory becomes trivial, can I now say something interesting about the dynamics that goes on? Because I think the world outside is not just interested to hear whether or not we can prove that there exists certain kind of invariant measures of certain type. They want to know what we can then do with it. So in some sense, maybe the random systems approach jumps a certain problem there, but it really confronts the next one, which is also an important problem, to talk about what is the dynamics of complicated systems with complicated behavior, even if the one-point motion is easy to understand. Anyway, so that's sometimes a trick. So, and I will give you an example of a system where precisely this trick will be used to go for a situation that is mathematically almost intractable to a situation which is mathematically completely tractable, and what we just do is just add a little bit of noise. And we don't change anything to anything. So for a physicist or applied scientist, it would make no difference. So here's my experiment of something that is maybe interesting complex system. So maybe I talk about, you know, critical decision complex systems. So this is a type of heterogeneous model where I have a network, and the network is represented by all these dots. So this is a program here written by Francesco Ricci, was a PhD student. And on each of these nodes, there is hyperbolic dynamics, an expanding map on a circle, 2x mod 1. So it's very chaotic. And we couple them in a way which I will explain later, in such a way that we have two nodes which are highly connected to many of the nodes, and the other ones are much less connected. So it's very heterogeneous in that sense. We have two nodes which are extremely connected, and the rest is not connected almost in comparison. Of course, this is a finite example, but our theorems will be about limits. And so what you want to know is basically what's the dynamic. So what's plotted is the two nodes here in the middle. They have a color, and this one has always the color blue. It's so-called phase 0. These are all circle maps. And the other one, and all other phases are relative to this nodes one, even though this one also, of course, jumps around. And you see then the colors going around if we simulate this. And we're particularly interested in what these hubs do. So the hubs are the ones that are highly connected, and the other ones are loosely connected to each other and also to the hub. And you see some interesting behavior. So let me just run simulation here. So the parameter value, let me see which parameter value. Oh, no. Did it get stuck? It got stuck. Maybe I quit it and run it again. What could I do? Here we are. So here, a small coupling. So alpha is the coupling strength. There's a coupling strength in this model. This says how the things are connected. So here we see. I don't plot the graph, but this is easier to see. So I see here that basically, so this is always fixed because it's just the gauge point. So this is phase 0, and all the other ones are relative phases. And you see basically that things that just blink, going around, maybe make a longer orbit. And you can see it going on a little bit more. And so from a finite dimensional, from a dynamical system point of view, this is a very difficult problem. It's like a very high dimensional system, and I make it easier, of course, that I make all these things uniformly hyperbolic. That makes it a bit easier, but I make it connected in a way which is complicated. So we basically have some chaotic behavior. In some sense, I don't see much order. Now if I drag up the parameter, that's 0.3, for instance, let's see what happens here. Now you see something happening. Now I see that everything starts blinking, but the two hubs are equal. So these are expanding maps on the circle. These are highly connected, these are loosely connected. And now this guy has synchronized with this one, but the rest is just going around like a madman.
Expanding maps on the circle.
Plus a linear coupling for each node, and then they make a coupling. They interact through some linear coupling, some coupling. I will give you the formula soon. Yeah.
By the network you are.
On the network, yeah. So there's a network. You can plot the network. You can see it's rather unappetizing. Here, plot links. Oh, it's changing the iteration. Let me. Maybe I want to not change the configuration. Fix the configuration, which is randomly chosen. And you see still here that we have. You see a little bit of fluctuation, but it's very close here. It doesn't really explore all the colors at all. And apart from that, it's just carnival. Okay, so what I did, I cranked it up from 0.1, it's a weak coupling, where I had no synchronization, to 0.3, where I have some kind of synchronization. And now I crank it up further. More stronger coupling, 0.8. And see what happens. And if I do stronger coupling, it again desynchronizes. So stronger coupling is desynchronized. So this is a highly nonlinear effect. So I have a complex network, and there seems to be some intermediate range for which I have synchronization. If I couple very weakly, I don't have synchronization. If I couple too strongly, I also don't have synchronization. So this is a typical kind of complex system problem. Lots of things, the network was not known. I just chose it randomly from some kind of graph properties, just to make sure that these guys are not very well connected and these are well connected. And then I look at the dynamics and say, can I understand this? Okay. So the phenomenon is called hub synchronization. And it's supposedly a toy model for understanding what's happening in the brain. So in the brain, we have neurons that are very well connected and some are not so well connected. And what we see in experiments, or what other people see in experiments, is that we have certain kind of levels of synchronization in the brain, but not too much of it. So it's very bad if you have your brain going synchronous, because you will get very ill and you don't live very long. So it's very bad. So synchronous behavior is associated with many diseases in brain. But what we see is that the thought processes and other things usually have to do with partial synchronization. So there is organization, so sometimes things synchronize, but they synchronize only on subnetworks. But the question is, how can you understand in a very complex network that you have such behaviors? And this is just a part of trying to understand these kind of things. Right, so we have poorly connected ones and very well connected ones, and the hubs in the network demonstrate coherent behavior, which are more connected. Okay, so the dynamics on each node is, I have a pointer better. The dynamics on each node is precisely this circle map. Oops. Sorry, I'm jumping around here. That is very well-known dynamics, just to keep it as easy as possible. And then we have this interaction term. So we have circle map plus something that interacts, and this interaction will be just linear. It will be just the difference between states. So I think that we have, I didn't write down here, but that's the difference. So it's a matrix. So it's a matrix coupling with the constants. So what's important is that somehow the strength of the coupling goes down with the number of nodes that we have. because it has to kind of basically, we have to have overall strength kind of blow up. So in some sense, when we take the limit to large system size, then the coupling gets weaker everywhere, but we still have this kind of phenomena. So how do we attack this? Typically, is to do some kind of like mean field reduction. So this is the physicist way to do it. So you say, well, we have some kind of coupling, and what we do is we just basically average this out. We say that, well, every node, the well-connected nodes, they see kind of the same neighborhood somehow. They get the same signal in. And what is the signal? Well, the signal is something averaged over what we believe some kind of invariant measure. So what invariant measure is that here, the reference measure is the measure of the single expanding map, which is a Lebesgue measure on the circle. So we just believe that if we look around at the oscillators, because they're weakly coupled, that they behave in an erratic way, and that what we get from them is just basically measured by this Lebesgue measure. And if you do that, you can calculate this interaction term with a given term here, and it gives you some term, and then you get a mean field equation. So this is what physicists usually do. And then you say, okay, lo and behold, we have this behavior for the hub. And if you look at the dynamics of this mean field equation for this example, you see precisely this behavior. This is a deterministic map, and it's a circle map. And so what we see here, indeed, we had chaotic behavior for small coupling. We had, again, chaotic behavior somehow for high coupling. And in the 0.3 range where we just have a fixed point. But now, of course, this mean field approximation is not really the real dynamics. It's some kind of like caricature of the dynamics, because the mean field, there's no mean field that you see. It's definitely not a static mean field. So the question is like, can we understand if the real equation of motion are like this, that we write it as mean field plus something, and this something is something that we didn't mention. This is the real term. So we just model the dynamics of this, and this is then modeling actually the real effect of the network. So I hope that on average, this will be on average be 0, because this should be the trend somehow, because they come from the mean field. The question was, can we prove this kind of behavior? Can we prove that we have this mean field correction? So if we can prove this, and this would be some kind of random term, then actually I see that my real model for the hub is a random dynamical system. So it says that it's not a mean field approximation. It says that the real dynamics is a random dynamical system where the static part basically is the mean field plus a kind of well-defined other term. So what you want to try to do is to prove something about this thing. Okay, the strategy is just to analyze the typical behavior, and the main challenge is to get the statistical description of this psi, because it just depends on the whole network. I can't say much about it. It just depends on the initial condition, depends on lots of other things. Can I get to grips with this? So the strategy of the proof that we follow here is to use uniform hyperbolicity of the node dynamics. So I know that all these things are expanding circle maps. They're uniformly hyperbolic. What that means is that if I make small perturbations, that the dynamics is so-called shadowable. That means that we have almost the same dynamics under some perturbation. If you have a uniformly hyperbolic system, if I perturb it a little bit, it will be almost the same dynamics. Now that's nice from a topological point of view. So topologically they're the same, but on a measure point of view, this is not necessarily the same. And this is a huge problem. So if I talk about measures, then we know that topological dynamics and measurable dynamics are completely different animals. So if I have stability on the topological side, I don't know that if I perturb it a little bit, that it's really true that I still have more or less almost Lebesgue measure on these circles. It might be that the connections and the dynamics conspires together in a certain way, in which I basically have very different behavior. So I'd like to have some kind of shadowing result for the measure. I want to make sure that this measure also is controllably close to the measure I had before. And this is precisely the problem. So it is very difficult to prove for such a system that the measure will behave well. There are some kind of nightmare scenarios you can think of, where you can say that the whole system could conspire against pushing the measure, even on a small perturbation, in a completely different direction.
So
So Matteo Tozzi, who works in the Imperial College, did a PhD there, he worked on this problem, deterministic problem, and he managed to show under some conditions, and one important condition was that the mean field equation is hyperbolic, is uniform hyperbolic dynamics, that in that case, you can prove that there is some good behavior. But I'm interested, for instance, in bifurcation behavior of the hub, and then I cannot use such a result. But what happens now if I add a little bit of noise, a little bit of diffusive noise? So I add a bounded noise of diameter epsilon for any epsilon. Epsilon can be as small as I like. As soon as I do that, I have complete convergence of this process. So so I can, by arbitrary small noise, I can regularize this behavior. I can make sure that this measure behaves in a good way just by adding a little bit of noise. And that's a real trick. So the trick is to go from the shadowing property, which is topological, and I want to also this hold for measures. And I can get this by just adding a little bit of noise. And maybe this is a bit of a trick, but you could also say that's actually very smart. So, because if we have this addition to the model, so this is a model of a complex system, there's lots of things that are here not so clear. If you ask a physicist, I add a little bit of noise, or I don't add a little bit of noise, which shouldn't be a real problem. But one of the models, I can really control the behavior, and I really get the behavior that you also see in the computer and you probably see in reality. Whereas in the other model, I get really stuck on the mathematics, and I cannot prove what I wanted to prove and what I see. It's just impossible, because I can see that if I try to prove it, that there will be some scenario that I can't avoid, and I can't really prove it. And so the two strands of thought, one is that you try to prove things, but you have to give strong conditions, otherwise you can never prove things, and it's very technical. And there's a cheaper way, is by adding a very small noise, and all your problems disappear as snow for the sun. Now, I think if we do complex systems modeling, that we don't want to constantly hit our head against these kind of very complicated problems, because we really can't make any conclusion. You have difficulties to get further, because we can't write down a theorem. And on this side, we could write a theorem about hub synchronization exactly. Now, in this complex systems world and network dynamics, there are very few theorems that people prove, precisely for this problem, because you have some large network which is connected in a complicated way. What can you do? I think the usual approach is you say, well, it's a mean field or whatever, and you just work with the mean field model. You don't even worry about anything else. But I think with a little bit of work, when we randomize it, and we use random dynamical systems ideas, we can maybe make proper theorems that not only take care of the average dynamics, but also take care of the fluctuations, and really have a proper random dynamical systems model of a complex systems, also in reduced form. And that's very powerful. Okay, so why did I want to give this example? Just to make another case for random dynamical systems, not just low-dimensional systems because it's just fun to play around with, or because of critical decisions, but I think they're interesting models that can be attacked by this strategy, that if we randomize a high-dimensional system, that we have a better chance to find low-dimensional reductions, and for instance prove that the exactness of mean field results, and not just mean field results on average, but that we actually can control the fluctuations on the mean field. That means we get a mean field equation plus fluctuation term. This is not a mean field approximation. This is the real dynamics. The real dynamics is a mean field plus a noise. Anyway, that's what I wanted to add. As I had the time, I thought today to say something about that. I think this is another line of thought, I think, which is should be very fruitful in complex systems, and so I think that we can actually do a lot of things with this. Okay, so now I want to come back to the end of the lecture in some sense, and summarize what we did. I thought maybe that's a good idea. If you had missed something, then... So this is what I think that I was talking about, and maybe you can then agree or disagree. So I think what I tried to do in the first lecture is to introduce the concept of a random dynamical system through an example which could be computed completely by hand. So this is rare, and it has also non-trivial dynamics. So the contractive iterative function system can completely be understood through some symbolic dynamics, and we can illustrate all the concepts that we use in random dynamical systems on such an example. So I hope that actually made it a bit more tangible, the objects that we talk about in random dynamical systems, rather than some abstract formulations. Then in the second lecture, I formalized the concept into more like a random dynamical systems theory, and then we applied this concept into random circle homeomorphisms or circle diffeomorphisms. And then we saw that despite the fact that these maps were not contractions, we still see similar behavior. So importantly, we see in the uniform contraction case, we had a convergence to a random fixed point. And also on this these non-contraction maps, the circle maps, we also got a contracting fixed point, but not in such a strong way. So we had uniform contraction here, we had non-uniform contraction here. But you could still also show that Lyapunov exponents are typically negative through Legendre results. And we have point attractors. And we also had a glimpse at the two-point motion to look for these conditions of contractibility for synchronization. That is another tool that I like. In the third lecture, we looked at random dynamical systems generated by SDEs. And we showed that basically, although the SDE is a more abstract concept, you can make it concrete by making a model for the noise through which it becomes a random dynamical system. And then we can basically carry on the same kind of analysis as we did before. We have similar objects, and sometimes, of course, we can also use stochastic calculus in that context because it's still the same kind of system. So we have information about Fokker-Planck equation and all kinds of things, but we can also think about it in a dynamic way. And then I gave some one-dimensional examples to look at. I also gave, of course, a high-dimensional example to show that we have non-trivial Lyapunov exponents and very complicated dynamics that, as far as I understand, no one really understands very well at all. Okay, then in the fourth lecture, I looked at systems with bounded noise, and I also argued why I think that bounded noise is an important class of noise that we should consider. And in that case, we are interested in minimal invariant sets for the associated set-valued systems because they carry stationary measures. So if I want to understand how regions with stationary measures interact, set-valued description is the reduced description and gives us a hope of doing something with less effort and still saying something about the random dynamical system. So I looked at some examples and I gave some elementary results about parameter families of invariant sets and how they behave if I change parameters. So how the parameter sets evolve, and then we could show that bifurcation patterns can be characterized in certain ways according to the theorems. And then finally today, I tried to kind of link back these basically toy models. I worked all the toy models into some kind of like larger scientific problem of critical transitions, and yeah, to see kind of basically where we are and why we maybe are doing these kind of things rather than a pastime, and because it's fun to work with, which is also true. So yeah, thank you very much for your attention, and it was a pleasure to do this course here. Thank you very much.
So if you have any questions, still have some time. So in 2 weeks, we're going to workshop here.
That's right.
So there are more talks from Jeroen and Martin as the same family. So if you are interested, please also come. Okay, so let's thank Jeroen for nice
Okay, thank you very much.
lectures.